All right. So most of you all of you in Tavernetti's class have a midterm on Friday, which I imagine you're well aware of. For those of you in Lee's class, you have a midterm next Wednesday. I finally just got added to his Canvas, so that's great. I know he doesn't typically give practice exams for Lee. I do have his exams from last time he taught 16B. I posted the first one. The first one he wrote is not very nicely written. Like it's like 4 problems that are kind of longish. So if you're in these classes and you're looking at that, whether or not you're in these class or not, I encourage you to look at that practice exam. I'll post the solutions in a little bit. But I would say you might not expect your actual exam to look like the practice exam I posted for Lee if you're in his class, because I think his exam writing got better as the quarter went on that quarter. So the second one certainly looks a lot nicer. What else to say? There was something else to say. I think we can on Thursday maybe go over the practice exam for Tavernetti. It looks pretty reasonable. I would say that said, we can certainly go over problems like it today if people feel like doing that. I was thinking about doing a few different things, including graphing to a large extent, because lots of people ask about graphing. There was one other thing I wanted to mention. Oh yeah. Yeah, looking at his practice exam, I'm pretty confident I can come up with something similar. So I'll try to write another practice exam that's similar to this that he gave you all by tomorrow. So, and I'll post that in Canvas, and I guess I'll post solutions as well before Thursday. Okay. Tavernetti practice exam today. Yeah. And solutions by Thursday. Yeah, that shouldn't be too hard. You should definitely do the practice exam. So I would say, looking at the Tavernetti practice exam, it looks reasonable in length. I think this would be a perfectly normal exam to give you all on Friday. Like he give you this actual exam, that would seem totally reasonable to me. Couple things I noticed. So just say a few words. 2 things I noticed. Thing 1 was that for problem 4, it says to sketch this graph. I think that means you don't have to do a whole lot, right? You have to get the general shape. It's your usual exponential shifted down by 4. You probably have to throw in the horizontal asymptote and then the tangent line. But I don't think he means like give a detailed graph, because on the first page he says, sketch this thing and list all important features. So I would be aware of that difference. The other thing I noticed is there weren't any derivatives like where the base and the variable both had or the base and the exponent both had a variable in them. There wasn't like an x to the sine of x or something like that. Doesn't mean it couldn't appear, which would require logarithmic differentiation. I just didn't see it anywhere on his exam. You might ask if it's going to be on your exam or not. I'm sure he would be as forthright as he could be about whether or not it was going to show up. All right, let's get to the specific questions people asked, and then we will get more general with the graphing, I think. As always, you're welcome to ask for things in class or ask questions, say like, can we see something like that? And happy to do my best to accommodate. But before we go anywhere, there's like 3 or 4 problems from the textbook people asked about, so I will get to those first. The first one being something similar to, this one's always a challenge. Co-16B, yeah. That's a B, believe it or not. And today is the 23rd of January. So the question was I don't like this phrasing, but I'm gonna phrase it this way. Find, that one, I'm gonna start over there, sorry. Given y equal to c e to the kt passing through the points, and yeah, we'll do say 1, 18 and 3, 2, find y. I don't love the way this is phrased, because what they really are asking you to do is find the model, find y. The question is find c and k, and then write y equal to number times e to the number times t, whatever the c and the k values are. So it just feels it feels like the instruction could be more clear. But you know what they mean now, right? And I think he writes it on your exam like this as well. Like for problem, and the practice exam problem, I think 5. Yeah, let y equals e to the kt. Given 2 points, find y. You know what you have to do, but I feel like the instructions could be nicer. Anyway, it's really easy to do this if one of those t values is 0. Notably, neither of those are. So it's harder when one of them is not 0. Let me just point out, no, we'll do this. Yeah, we'll do the hard one. So in this case, you don't just get C automatically. Normally be like, okay, C is whatever the y, like if you had 0,7, C would be 7. Here, you can't do that. So you have to start off by actually using both values, meaning we're going to write both. So I'm going to plug in 1 for t and 18 for y. So 18 equals c e to the k times 1. I probably would just write k. I'm also going to then plug in 3 for t and 2 for y. So 2 equals c e to the k times 3. Do make sure that when you're writing this, that you're getting the order correct. The input is the t or the x, and that's always first. So this is a t comma y. Are these points here. 1 comma 18 and 3 comma 2, or x comma y if you're using an x instead of a t. At this point, there's probably 2 different ways you could go. The slicker way of doing this, like the faster way of doing this, is to divide these equations by each other, which I always feel like feels like trickery personally. Like if you, so you could, I'll just point out, you could divide, and 18 divided by 2 is 9. And c e to the k divided by c e to the 3k. Well, I'm just going to write that because who wants to do all that? The c's do divide to 1. And when you have e to the k divided by e to the 3k, what do you do with those exponents? It's not a rhetorical question. They don't cancel out, they subtract. And k minus 3k is negative 2k. So we could totally rewrite this as 9 equal to e to the negative 2k. Before we go any further, let me show you the way I would probably more normally think of it. So I usually don't think to divide these things. It's just not the way I operate. What I would personally do instead is solve each of these equations for c. So I would write this first one as 18 divided by e to the k equal to c. And the second one as 2 divided by e to the 3k. I do like to write the 3 in front of the k instead of the k in front of the 3. Doesn't really matter though. Equal to c. And then I would set these equal to each other. So then I would get 18 over e to the k equal to 2 over e to the 3k. I usually kind of, at this point, awkwardly cross multiply, even though it's probably somewhat a waste of effort. It's still what I do. I would write 18 times e to the 3k equal to 2 times e to the k. But then I would really bring all my k's to one side and all my not k's to the other side. So I would divide both sides by 2 and say 9 e to the 3k equals e to the k, and then divide both sides by e to the 3k. And get exactly to the place that I got to by dividing both sides by each other. So I end up getting 9 equal to e to the negative 2k. Notice that I do get the same result, the same equation, either way I do it. Whatever you prefer, or whatever makes more sense to you is what you should do. Again, you only need to do this if neither of those initial points are a 0 comma something. In his practice test here, in problem 5, you wouldn't do it this way, right? You're given a 0, 3, that means C is going to be 3, and it's easy to find what K is after that. And we can do one like that too if you all would like. At this point, then we have to solve for K. I've got 9 equal to e to the something. I'm going to take the natural log of both sides. So I'm going to rewrite this as the natural log of 9 equals, I'm not going to write the natural log of e to the negative 2k. I'm just going to write negative 2k. Because we know that taking the natural log of e to the something is just something. And finally, k is going to be the natural log of 9 divided by negative 2, or I would probably write the negative out in front, right? Is negative natural log of 9 divided by 2. We're not done. Now, and this is probably the one part of this where this way of doing it, where you solve for C, is slightly more useful in that you then have to plug back K in so that you can find C. So I'm going to plug K into either one of those. It doesn't really matter which one you pick. Here, I would say that 18 over e to the K1 is slightly nicer to plug into, but again, either choice is fine. So plugging in to find C, we're going to get that C is equal to 18 over e to the K, negative natural log of 9 over 2. Sorry, it's kind of small. And technically, you could just leave it like that. That does simplify into something, not really. I mean, yeah, sure, I guess. Yeah, that simplifies into something nicer. I will show you just for the sake of showing you, but I'll tell you, if I was taking an exam, I wouldn't bother, and I would just write my final answer, which I don't really have room to write. I guess I'll write right here. My final answer is going to be y, right? Because I'm asked to find y equals this C value, 18 over e to the negative natural log of 9 over 2. It's terrible. Times, that's C, right? E to the K T. Gross. But that's a perfectly fine answer. Now I'll point out, because I think it's worth pointing out, that e to the negative e to the negative natural, no. Can I say natural log of 9? Almost. E to the negative natural log of 9 over 2 is simplifiable. You could write this as 18 over, check this out for a second, e to the negative 1/2 times natural log of 9. And then that negative 1/2 can come up as the power of 9 in the logarithm. You can write this as 18 over e to the natural log of 9 to the negative 1/2. What's 9 to the positive 1/2 power? What's 9 to the negative 1/2 power? You're right. So e to the natural log of some stuff is just the stuff. So this is really 18 divided by e to the natural log of 1/3, which is 1/3, which ends up being 54. You don't need to do any of that, I don't think, but I just wanted to tell you that that is something that often happens with these problems, is the e to the natural log of whatever ends up being some nice-ish kind of thing. But again, if this is an exam situation, I would totally just leave it like this. Not bother with any trying to simplify unless specifically asked to do so. Just for the sake of me, I'm all zoomed in. Sorry, I'm sorry. Wow. Okay. How did I get way over there? What did I do? I don't know how I got so far in that one direction. I feel like I'm way zoomed out. I don't love this. Apologies. Okay, that's all right. Sure. Okay. Just for the sake of completeness, if you were given one of the easier ones, right, it's much easier. So just for example, if instead you were given, say, something like y equal to, let's use an x instead, c e to the k x with points, say 0, 7 and 8, 23. I don't think you need to show any work personally to know that c is equal to 7. But you can, or you can plug in 0 and 7 and get 7 equal to c e to the k times 0. E to the k times 0 is 0, e to the 0 is 1, so you end up getting 7 equal to c. And then finding k is relatively straightforward. Our new model is y equal to 7 e to the kx, and then we plug in this other point, and we get 23 for y equal to 7 e to the k times 8 for x. And then we can solve for k. Divide both sides by 7. I like to write 8 times k, not k times 8. Doesn't matter though. Take the natural log of both sides. Natural log of 23 over 7 equals the natural log of e to the 8k, which is just 8k. And finally, well, not finally, but solving for k, I get the natural log of 23 over 7 divided by 8 equal to k. And then we go back and write what y is. So we get that y is equal to c, which is 7, times e to the k, which is this gross number over here. I mean, I've disparaged irrational numbers. Oh, then that's an x, not a t. Sorry. So y equals 7, e to the natural log of 23 over 7, 8 over 8 times x. And I might put that in parentheses just so that we know it's all in the exponent there. Right, see how that's a lot less work if you have 0 as one of your x inputs or your t inputs? Yeah.
How did you get 7 into C?
So what's k times 0? What's e to the 0? So I have 7 equal to c times 1. But really, generally, right, if you have 0 comma whatever, that whatever number, if it's paired with a 0 for x or t, that is your c value always. Because this will always happen. You always get c times e to the 0, and so whatever the y value is when x or t is 0, you're going to get that for your c value. That's why that constant in front is often called the initial value. It's all sometimes written as c naught or y naught or whatever sub 0. Other questions about this particular situation? All right. So many things. I guess graphing. Yeah. Yeah, let's talk about graphing. So there's lots of different graphing types of things to be aware of. And I imagine, well, yeah, looking at these things you have to graph, yeah, exponentials. So let's talk about graphing. Oh, I know, I had some, yeah. Papers everywhere, you know, it's, oh, that's a good one too. Cool. Yeah, let's do a couple of these. So let's graph some easy exponentials, relatively easy. Let's say we're going to graph f of x equal to 3 to the x plus 1 minus 9. So when I'm thinking about this graph, I'm observing a couple things. One, usual exponential shape, right? It's an exponential, it's 3 to the x or 3 to the x plus 1, whatever. It's going to be increasing in the usual shape from left to right. If it was 3 to the negative x, it'd be decreasing from left to right, but it'd still have the same typical shape, just flipped. So usual shape, that minus 9 means we are shifting down by 9. And this x plus 1 means we're going to be shifting left by 1. For exponential functions, I don't really kind of think that much about the left or the right shift. I just kind of accommodate as I go. Whereas the vertical shift does matter more. The vertical shift in an exponential function is going to change where my horizontal asymptote would be. So normally, a regular basic exponential function would have a horizontal asymptote at y equals 0. This one's going to get shifted down by 9. So a new horizontal asymptote is going to be y equal to negative 9. In fact, I'm probably just going to start by drawing that. Here's my usual xy axis every time. And then sure, negative 9 is maybe down here. And I could probably draw the thing at this point. I could be like, well, it's going to have the usual kind of shape. I might find a couple more pieces of information, but really I shouldn't. I mean, I'm going to because I should, but I shouldn't worry about what they actually are when I graph it. My graph doesn't need to be perfect. It just needs to be a sketch. So here's my graph. I know it's going to look like this. Maybe not my best work ever. It's okay. It's got the usual shape. And I see there's a y-intercept and there's an x-intercept. An exponential function won't always have an x-intercept because you might shift it up or not vertically at all. But if you do shift it down, you will end up getting an x-intercept. On the other hand, an exponential function will always have a y-intercept because we can always set x equal to 0 and get a value for y. So if I was trying to graph the important pieces of this function, I would find my intercepts after the asymptote is probably the most important piece of this function, like other than the function itself. Just like with logarithms, the asymptote is kind of the most important feature. After the asymptote, I would find the intercepts. So how do we find the y-intercept? What's the usual thing we always do to find the y-intercept? Right, we set x equal to 0. And if we do that, well, I'm just gonna plug in, I'm gonna get, ooh, so I see what, so one thing I should have done though, before I graph this, it's not gonna be a problem here, but I should have made sure that my y-intercept was actually below the origin, right? I could have had something that was like something wild here where it actually ended up being, even though my horizontal asymptote's so low, it could have like crossed here and been like way up there. So I should have been not quite so presumptuous, but it'll be okay. So 10x equals 0 and f of 0 is going to be 3 to the 0 plus 1 minus 9. 0 plus 1 is 1, 3 to the 1 is 3, 3 minus 9 is -6. So there's my x-intercept at 0, -6. Does it actually look like it's -6? Not really. It looks like it's kind of halfway between 0 and 9. Nobody is checking. Nobody cares, right? As long as it seems reasonable, it's fine. Let's go ahead and find the x-intercept. Just like we set x equal to 0 to find the y-intercept, we're going to set y equal to 0 to find the x-intercept. So setting y equal to 0 or f of x equal to 0, 0 is equal to 3 to the x plus 1 minus 9. This is where we are fortunate in that both 3 and 9 have a common base. I would write this as 9 equal to 3 to the x plus 1. And then if I didn't know right off the bat, I would rewrite this as, well, 9 is 3 squared. And if 3 squared is equal to 3 to the x plus 1, the exponents have to be equal to each other. So we can say, oh, that means 2 has to equal x plus 1, or 2 minus 1 is equal to x. So my x-intercept is 1. So my point is 1, 0. Again, does it look to scale? No, I don't care. You shouldn't care either. As long as it's reasonable, you should be fine with your graph. No one's gonna look at that graph, and I don't think anyone will look at this graph and take off any points for anything, unless there was something specifically mentioned that I didn't answer. But as far as I'm concerned, I've graphed it as nicely as possible. I've plotted the points that were important. That's it. Yeah. Yes, definitely. So the original, so I would say the original function is 3 to the x. So if I graph the parent function, y equal to 3 to the x, and I'm going to graph it dashed just to kind of make it less important. So here's where I probably should, it would be nice to have a better scale if I was graphing another function as well. But 3 to the x basically just looks like this function, but not shifted at all. So yeah. So it's going to look like, yeah. If I had known that was going to be a question, I would have paired differently. But it's going to look like this. It's going to go through the point 0, 1. And I don't think they should actually intersect each other. I guess it's possible. No, maybe it's, I guess it's possible because we have a left shift and a downward shift, but it's probably, they probably don't intersect each other. So basically from here, I would shift this function 1 to the left to this point 0, 1 would shift 1 left to -1, 1, and then down 9 to -1, -8. So that point moves 1 to the left and down 9. I do like to think about, although I didn't obviously talk about it when I was graphing this, but I do like to think about kind of where the y-intercept moves to if I'm graphing a exponential function, or where the x-intercept moves to if I'm graphing a logarithmic function. Other questions about this? I would say definitely the exponential and the logarithmic function. So just to make sure everyone's on the same page. And we come back to this if we need to. It's in order here. The graph shapes you should definitely know. Aside from like, well, say the graph shapes we should know for now are the exponential. And the one that everyone's going to refer to if they're graphing an exponential is y equal to e to the x, or f of x equal to e to the x. Of all the exponential functions, that is the one. Is the best. Why is it the best? That because You've got, even though you can't quite as easily see it because it's on the x-axis, but we do have a horizontal asymptote at y equals 0. Horizontal asymptote, y equals 0. I'm not going to write it down, but I am going to note the domain is everything. And the range is all positive numbers. I might write it down, but I'm not going to write it down yet. So on the other side of things, literally the inverse function is the logarithmic function. G of x equal to the natural log of x. And again, really, this is any base is really valid. These are just the typical choices of bases. But I will point out, whether I was graphing e to the x or 2 to the x or 3 to the x or 5 to the x or 10 to the x, my graph would still look like that. It would still have a horizontal asymptote. It would still go through the point 0, 1. Yeah, it might look steeper or less steep, but if I'm only graphing one thing, I'm not graphing it against anything else to compare it to, so you can draw it however you like. I would draw this, I would literally, like, if you asked me to graph 5 to the x on a different piece of paper, it would look exactly the same as that, even though maybe it should look a little bit different. No one cares. I don't mean to be like glib about knowing, but no one cares, right? Really, like no one's gonna look at your paper and be like, oh, they didn't like get the curve steep enough at the origin, I'm gonna mark them. No, nobody cares if your curve looks exactly right if you're graphing an exponential function. It just has to be in the realm of reasonable. Similarly, for the logarithmic function, I mean, I care. I hope it looks good. But not perfect. You shouldn't spend that much time making your graph look perfect. You should spend just enough time to make it good enough to get all the points and then move on. So here our logarithmic function is literally the inverse of this. It looks like that graph reflected across the line y equals x. Has the intercept of 1, 0, and we have a vertical asymptote at x equals 0. If you really, really care, you're allowed to label one more point on each of these graphs. You could label the point 1, e, right? If you plug in 1 for x, you get e to the 1, which is e, which is about 2.7, but you should write e. And over here, you can label the point e, 1. But you don't really need this. Unless you're asked to, right? All of this is under the caveat of, unless someone asks you to do it, then you need it because someone asked you to do it. So I'd say of all the graphs, these are the two you need to know for this exam, right? These are the two graphs you should have memorized. Yeah, there are other things you should know from last quarter, like graphing y equals x squared, or any kind of line, or y equals x cubed, or the square root of x, or the cube root of x. Like those are pretty typical graphs in our wheelhouse of things we have seen before. But I don't imagine they're probably appearing on this exam. So. And then maybe sine and cosine graphs you should also be aware of. But like, again, I don't think they're showing up on this test. They should just be things from the past. Okay. Okay. Yeah, that's, to me, that's, and then again, right, this could be 3 to the x, or 5 to the x, or 7 to the x. And this could be, or log base 2 of x, or log base 3 of x, or log base some other, 10 of x. I should have just written log of x, right? Any of those graphs, any of those functions would be equally suited by graphing this. Okay, there's one more thing you should know how to graph that I just thought of, but it's really one of these graphs. It's just, so the kind of funny thing I would say is that we definitely talk about graphing like e to the negative x, or no, yeah. So we should also be able to graph, say, f of x equal to, I'm gonna actually say 2 to the negative x instead of e to the negative x, because I want to point out that this is the same as f of x equal to 1/2 to the x. And the only difference between this graph and the previous exponential function is that instead of increasing from left to right, it is going to be decreasing from left to right. So this graph has the same shape, just reflected across the y-axis. So this graph still has an intercept at 0, 1. Still has a horizontal asymptote of y equal to 0. And I'm not as good at drawing this one, just to be perfectly honest. So it's not going to look as good. Well, maybe it will. We'll see. It looks like that. It decreases from left to right, but still has the usual exponential shape. We have the point 0, 1. And I guess if I really wanted, I could also have the point 1, 1/2. These types of functions also do come up graphically, so yeah, they're probably worth mentioning. See here. Oh yeah, that was a good one. Okay. We could spend all the rest of the class talking about graphing. Like we don't have to, but we certainly people, if that's what we want to do, we can do that. So I have a few more graphs in mind that I want to mention, and then we'll see how we're feeling. Someone asked about question number 35 from, I don't remember which section it was, to be perfectly honest, from one of the sections with graphing stuff. Here's the function that they asked about. And I have other ones like this, but this one seems like a perfectly good one. So here's number 35 from, I don't remember which section. It's to graph f of x equal to 8 over 1 plus e to the negative 0.5x. So when I hear the word graph in a calculus class, what that means to me, and this might not be correct, is that we should graph the function, including all intercepts, asymptotes, extrema, and inflection points. I don't think that is what this question is asking us to do. I don't think we're being asked to find extrema or inflection points, but yeah, I really don't think that's, and I don't think that's what he's getting at either. Yeah, no. I don't think any of these graphing questions on the practice exams are asking about that particular portion of what a usual graph would have been like in 16A, right? Where we're at the end of the quarter, we were graphing things and finding the first derivative and second derivative and finding the critical points and finding the maxima and the minima and the inflection points. So I'm not going to do that here, even though normally I would be like, yeah, we should find those things. So yeah. Although that said, there is a question on this. Yeah, he definitely lays it out in question 1, part B. Graph this thing, x e to the x, and find the first and second derivatives, and find the sign charts for the first, second derivative, and the original function, and find the maxes and the mins and the intercepts and the asymptotes. So I think if you have to do that, he's going to tell you to do it. Well, yeah, but not this one, because this is not a good problem for that. But yes, I definitely have a couple in mind. So not doing all that, sorry. We want to figure out. These ones always kind of, yeah. Oh yeah, I think he did one like this in class, and I feel like it was kind of weird, but it made sense to some degree how he did it. So here's what I would think about for a minute. I'm going to think about just the denominator for a moment. Think about graphing just y equal to 1 plus e to the negative 0.5x. Well, that's looking like an exponential function, but the negative there is going to do what the negative just did in the previous one. It's going to flip it across the y-axis. It's going to reflect it horizontally. And then the +1 is going to shift it up 1 vertically. So this is going to look something like this. I'm going to have a horizontal asymptote. Y equals 1. Again, this is for this part here. It's not the actual graph of the thing I'm doing. I'm just giving myself something to work with here. And then this graph here is going to be, well, the y-intercept should be, in fact, I don't need to say should be, I can find it. I can set x equal to 0. If x is 0, y is going to be 1 plus e to the 0, which is 1 plus 1, which is 2. The y-intercept is 2, and this is going down from left to right. So there's the shape of this denominator, which doesn't at all tell us about the shape of the graph, kind of. It just tells us that's what that looks like. So now, I can kind of look at that and get an idea of what my graph should look like, because if I want to graph f of x equal to 8 over 1 plus e to the negative 0.5x. Well, the first thing I would notice is that this function is always positive. Right? I'm always getting positive y values. It's never 0. It's never negative. Meaning 8 divided by that is also always positive. If something is always positive, you take the reciprocal of it, still positive. Multiply by 8, still positive. So this is always going to be positive. Great. So I know the whole thing's going to be above the x-axis. Above the x-axis. How do I say? Yeah, it's like, how do I say all the things that I know are happening here without like just doing them? Good question, James. He talked about doing horizontal asymptotes using limits, or not really. Like he's just been saying them, kind of. Yeah. So here's what I would say. We're gonna have some horizontal asymptotes. If the denominator is getting closer and closer and closer and closer to 1, the whole fraction should be getting closer and closer to what? Well, the denominator is getting close to 1, so the whole thing's getting close to 8 divided by 1. So one of my horizontal asymptotes should be y equal to 8. Because as x goes to infinity, 8 over 1 plus e to the negative 0.5x gets closer and closer to 8 over 1 plus 0, which is just 8. Or in other words, e to the negative 0.5x gets closer and closer to 0 as x is really, really big. Look at the graph of 2 to the negative x, or e to the negative x, or e to the negative 0.5x. Closer and closer to 0 as the x values get larger and larger and larger. If this part's getting close to 0, the whole denominator is getting close to 0 plus 1, the whole fraction is getting close to 8 divided by 0 plus 1, which is 8. Or as I might write, the limit as x goes to infinity of 8 over 1 plus e to the negative 0.5x is equal to 8. But I think there's also a horizontal asymptote to the left. Let's see what that is. Meaning, if we look at the limit as x goes to negative infinity of 8 over 1 plus e to the negative 0.5x. Something important to know. Two things I want. There's lots of things. Yeah. A couple things I think are important. Thing one, if your denominator gets big, your fraction gets, and vice versa. If your denominator gets close to 0, your fraction gets large. I say that all the time. The other thing is that e to a really, really big number is a really, really big number. Think about the graph. If x is really, really big for a normal e to the x graph, e to the x is really, really big. On the other side of things, if x is really, really negative, e to the x gets really small, really close to 0. Okay, so now the question is the exponent here really, really positive or really, really negative? Well, it's negative 0.5 times something that's getting negatively big. So my exponent here is actually really, really, really positive. So this thing here, this is essentially e to the infinity, which is infinitely large. 1 plus something infinitely large is still infinitely large. And then 8 divided by a really, really big number is big or small? Small. So this limit is going to be 0 because it's 8 divided by something big. Here's what this means. It means as we go to the left, our function is getting really, really close to 0. As we go to the right, our function is getting really, really close to 8. And I'm just going to kind of make up what's happening in the middle. So graphically, I have a horizontal asymptote of y equals 8 to the right y equals 0 to the left. I don't really want to try and draw as a horizontal asymptote. It's just there as the x-axis. And then, sure, if I plug in 0, I know that this thing, this denominator, if x is 0, y was 2. So here, if I plug in 0, I'm going to get 8 divided by 2, which is a value of 4. So it probably looks something like this. If I really, I don't. If I really wanted to find it, there's probably an inflection point to find. There probably is not any relative extrema. This looks like it's always increasing. But I would be willing to bet there's an inflection point, but I don't think anyone's asking you to find it. So that's how I would graph something like this. And I really think the important features here are the fact that we have horizontal asymptotes to the left and to the right. Okay. This is different than the problem he did in class. I can be more specific. This is really different because the problem he did in class had a vertical asymptote as well. I can say words as well. So yeah, let's look at one more like this. Because I feel like he cares about this example. I don't know why. I just have the impression that he cares about this kind of example. So let's do one more like this, and then we'll move on to something where we actually have to find critical points and stuff like that. Yeah, we'll do one more. So not that one. Let's make it a little bit less heinous. Let's say we want to graph f of x equal to, sure, let's do that. Yeah, let's say, seems terrible. Sure, okay, yeah. We'll try to make it look nice. 16 over 2 to the x minus 8. Yeah, that's kind of awful, but it's fine. Instead of doing e to the x, just to make it look slightly nicer numerically, we'll do this one. Now, again, I do think, but I'm going to credit to him. I think his tactic of graphing the denominator first was kind of nice. Like that's what he did in class, right? He graphed just the denominator part to see where you had like a 0, and then kind of flipped it, for lack of a better word, to see where you have asymptotes. So here's what I'm saying. Let's just think about what y equal to 2 to the x minus 8 looks like. Well, that looks like our usual exponential function. In fact, you all should graph it. Graph 2 to the x minus 8. That minus 8 is going to shift it. I'm not going to tell you. You get to figure it out on your own. It's going to shift it some direction. Also, if you haven't filled out the attendance form, do make sure you scan it at some point or have it already bookmarked and filled out. So if you can take that back if anyone else needs it, like you're welcome to grab those things off the wall. I don't care. I just collect them. Anyone else do? Okay. Yeah, grab it. Thank you. Appreciate it. All right, so 2 to the x minus 8 is the usual exponential function shifted down by 8. So we're gonna have a horizontal asymptote at y equal to -8. It's gonna look vaguely like this. It does have a y-intercept of 0, -7. Just plugged in 0 for x, and 2 to the 0 minus 8 is 1 minus 8. And it's got an x-intercept of how many? Show me on your fingers. What's the x-intercept? It is a whole integer number, so like half a finger. So if I set 2 to the x minus 8 equal to 0, or 2 to the x equal to 8, I better be getting x equal to trace. No, she's not here. Was that this class? Was that the other class? Sorry, one of the classes. I have 2 classes in this room that are like at the same time. So I never remember who's in which class, to be honest. Someone was like, I was like, what's your name? They're like, I was trying to remember their name like I often do. They're like, it's like the number 3. And I'm like, Trace? And then it was not, it was Trinity, was her name, but I could not get this. Anyway, it must have been the other class, right? It was not this class. Okay. Yeah, trying to make jokes that don't compute to anybody except for me. That's all right. So we got this point 3 comma 0 here. So here's what I'll point out here. This function is positive if x is larger than 3. It's negative if x is smaller than 3. And that's going to be true here as well. So if we start making the sign chart for this function, I didn't make one for the last one because it was always positive. It didn't seem like it was really necessary. But here I'll point out, first of all, my function is undefined at 3. If I plug in 3, I get 0 in the denominator. And then our function, if x is larger than 3, like 4, 2 to the 4th is 16, 16 minus 8 is 8, 16 is positive. Just like this is positive, right? You take the reciprocal of a positive thing, it is still positive. And over here, if I pick a number less than 3 for x, the denominator is going to be negative, which means the whole expression is going to be negative. Because 16 divided by a negative number is still a negative number. And just like last time, I'm going to look at the horizontal. Well, actually, I'm going to point out that this means we're going to have a vertical asymptote at 3. Right? This function is undefined at 3. We have not 0, 16 divided by 0. That means we have a vertical asymptote. If you have a 0 over 0, it's a whole other thing, limits from last quarter. But if you have not 0 divided by 0, I can't think of a time where you wouldn't have a vertical asymptote. So we have a vertical asymptote at x equal to 3. You plug in 3, you get 16 divided by 0. And then I might look at my y-intercept. My y-intercept would be 16 divided by 2 to the 0 minus 8, which is 16 divided by 1 minus 8. So it's a little, it's close to negative 2-ish. Or 16 divided by 7 is close to 16 divided by 8, which is close to negative 2. I'm not too worried about it, though. I'm just trying to get something on the board here. And then I'm really thinking about the horizontal asymptotes here. So let me ask everybody. When x gets really, really big, 2 to the x minus 8 also gets really, really big. Which means 16 divided by 2 to the x minus 8 is going to, thank you, it's going to get small. So we can say that in mathematical language here, the limit as x goes to infinity of 16 over 2 to the x minus 8 is going to be 0. The denominator is getting super large, the fraction is getting super close to 0. On the other side of the graph, as x goes way, way, way to the left. Well, in this denominator graph here, as x goes to the left, the function gets closer and closer to, I know I wrote 8 there, there should be a negative sign there. The function gets closer and closer to what? Right. So if my denominator is getting really, really close to negative 8, then the whole fraction is getting really, really close to 16 divided by negative 8, which is negative 2. So the limit as x approaches negative infinity of 16 over 2 to the x minus 8 is going to be 16 divided by negative 8, which is negative 2. And then we can probably throw together a graph. Let's see what we got. Maybe. So now I have a vertical asymptote at x equals 3. I know to the left of x equals 3, the graph is negative. To the right of x equals 3, the graph is positive. To the right, eventually I'm going to be getting closer and closer to 0. Right? Right? Yeah. So it probably looks something like this, since the graph has to be positive. Something like that. It can't come from below, because the graph can't be negative over on that side. And on the left side of 3, I know that if I go way, way to the left, the graph is going to get closer and closer to negative 2. It can't come from above because the graph isn't positive left of 3. It has to come from below. That question.
Can you explain the limit going to negative infinity again?
Sure. So I didn't actually do the limit in my head. Like what I said was, if I look at this graph, as x goes to negative infinity, What's the graph getting closer and closer to? Almost, right. So that means the denominator is getting really close to -8. And if the denominator is getting close to -8, the entire fraction is getting closer and closer to 16 divided by -8. The other way you could do this without graphing anything is by saying, well, I know what 2 to the x does, right? As I go to the right, 2 to the x goes to infinity. As I go to the left, 2 to the x is closer to. Think about the graph of 2 to the x. If you go way to the left, it gets closer to what horizontal asymptote value? 0. So what's happening is the 2 to the x here is getting closer and closer and closer to 0. And 16 over 0 minus 8 is -2. That's the way you can do it without actually thinking about the graph of the denominator part. So there's my kind of wonky looking graph. I don't really think he's going to ask about something quite as complicated as this to graph, but he could, right? You never know. Yeah. Right. So for the limit to infinity, exactly. So for the limit to infinity, and I'm thinking of I'm really thinking of what 2 to the x is doing. Oh, 2 to the x is getting infinitely large. So then a really, really big number, -8 is still a very large number. And 16 divided by a very large number is very small. That's what's happening there. When I have fractions, I'm always asking myself, what's going on with the denominator? If the denominator is getting big, the fraction is getting. And if the denominator is getting really, really close to 0, the fraction is getting big. Like here, right? When x gets really, really close to 3, 2 to a number that's really close to 3 is really close to 8, which means the denominator is really, really close to 0. And 16 divided by a super tiny number is infinitely large. It's really, really big. That's what's happening there. All right, but let's look at one of these ones where it's more like having to find all the things. Let's see. I don't want to do the one he has on the practice exam because that seems like we could save that for later. Maybe do that one. That one's terrible. Sure. Let's look at. Yeah, we'll do that one. They're both good. Well, we might do both of these. We'll see. We'll start with this one. Let's graph f of x equal to e to the x divided by x. And we want to find all the things. So the order I typically go in is first finding the intercepts. So I don't think there actually are any intercepts for this one, which is kind of annoying, but it's fine. So y-intercept, we would normally set x equal to 0, but we can't. Because if x equals 0, f of 0 is e to the 0 over 0, which is undefined. 1 over 0, undefined. That does tell me that we're going to have a vertical asymptote at x equals 0, but we're not there yet. X-intercept, we also don't have any, because we're going to set the whole thing equal to 0. But for a fraction to be able to equal 0, the numerator has to be able to equal 0. And e to the x equal to 0 has no solutions, right? You know the graph of e to the x, it never actually touches the x-axis, so it never actually equals 0. So we don't get any x-intercepts either. Bummer. Then I look at the asymptotes. I usually look at the vertical asymptote first. Say, okay, well, is there any place where I have division by 0 and not 0 on top? Yeah, I have a vertical asymptote at 0. Now I should mention there is one other way you can get a vertical asymptote. But usually you get a vertical asymptote when you have like something like 5 over x minus 2, and your vertical asymptote is x equals 2. The other way you can get a vertical asymptote without dividing by 0 is by having a logarithm. Logarithms have vertical asymptotes at the value of x that would make you have to try and take the log of 0. So real quick here, right? If I had y equal to the natural log of x plus 2, this would totally have a vertical asymptote at x plus 2 equal to 0 or x equal to -2. Vertical asymptotes always have, logarithmic functions always have vertical asymptotes at the value of x that would make it so you were trying to take the log of 0, which is not division by 0, but it has a similar effect. Okay. Sure, you go here, right? Let's go here. No, I'm all over the place now. I'll have to figure that out later. Horizontal asymptotes. I often, if I'm finding all the things, sometimes I leave this to the end. Here it's not, no, here it's kind of terrible. Yeah. So I'll point out that you have to look at the limit to either side. So look at the limit as x goes to negative infinity of e to the x over x. So as x goes to negative infinity, what's happening to e to the x? Think of it. I really encourage all of you. You should have a clear vision of what e to the x looks like when you close your eyes and look in your head. Or if that doesn't work for you, when you look at your right hand. So if you look at e, if you think about e to the x and you go way to the left, are we getting really, really big or really, really close to zero? Right. Okay. You should be able to see that without doing anything. You should be like, e to the x is there, it's there, it's there, it's right, it's that. Okay, so I know that the top is getting close to zero, the bottom is really big, and zero divided by a really big number is still zero. So we're gonna have a horizontal asymptote to the left. The thing that's challenging about this particular example is if you look to the right, it's not immediately clear. To the right, e to the x is really, really big. So does x. So you have a really big thing divided by a really big thing. Could be anything. This is an example where you would actually want to use L'Hopital's rule. But I don't think that's something that everybody covered in 16A, am I correct? Right, does that sound foreign to you? I mean, shit, it's a foreign name, but not really. But like, if that's something you haven't seen, that's not because you were supposed to have seen it necessarily. But the way we kind of usually justify this to ourselves is the exponential function gets bigger much, much, much faster than the linear function y equals x. This fraction is going to get larger and larger and larger. This limit is infinity, which means we don't have a horizontal asymptote to the right. The function just keeps increasing. Now, we'll come back to this and talk about how we could have seen this without having to actually do this limit when we talk about the derivative stuff, which we're about to do right now. So after you dealt with the intercepts and maybe the asymptotes, at least the vertical asymptote, maybe not the horizontal asymptote, then I move on to, I never like making the sign chart. It's not my thing. I guess you can make a sign chart for the function. So what's the only point I need to include on my sign chart in this example? Yeah, wherever you have a vertical asymptote or where you have an x-intercept. I don't have any x-intercepts. So 0 is the only place where the sign could change. If you pick a number larger than 0, like 1, e to the 1 is positive, 1, oh, you can't see that. E to the 1 is positive, 1 is positive, it's positive on the right side of 0. Pick a number like -1, e to the -1, still positive, e to the anything is positive. Think about the graph of e to the x in your head that I know is there. The denominator is negative though, so positive divided by negative is going to be negative. Great, so we know the graph is below the x-axis over here, above the x-axis over here, and we've got a vertical asymptote right there. Cool. Now let's talk about the first derivative stuff. So, I would use the quotient rule here. I don't think writing this as e to the x times x to the negative first and then using the product rule is a better way to go. I would use the quotient rule. It's going to be the bottom times the derivative of the top times the top times the derivative of the bottom, all divided by the bottom squared. When you're dealing with graphs and finding derivatives, you do have to simplify as much as possible so that you can find the critical values. I am going to point out that I can factor out an e to the x from the numerator. I'm left with an x minus 1 over x squared. If we set this equal to 0, we're going to get x equal to 1. I will also point, so our critical value is x equal to 1. I will also point out, like last quarter, for those of you that were with me last quarter, that x equal to 0 is what I like to call a pseudo-critical value. It's still important. The sign of the derivative might change there, and we should include it, even though it's not a critical value, because we know it's not a critical value because it's where we have a vertical asymptote, and you can't have a max or a min where you have a vertical asymptote. But we still want to include x equal to 0 in our sign chart. And I should take back what I said a minute ago. I like sign charts a lot. I just don't like them for the original function. I don't know why. I just never did them. I definitely think the sign chart is valuable for the first derivative and the second derivative. So let's make our sign chart. Got a 0, a 1, we're talking about f prime. Also, you want to factor as much as possible so it's easy to figure out what the sign of your thing is in each interval. Pick a number larger than 1, like 17. Either 17 is positive, 17 minus 1 is positive, 17 squared, well, anything squared is always positive, so it's a positive, 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 whole thing positive. You can keep doing that, or you can employ the trick where you look at the value, you look at the factor it came from, you look at the power on that factor, and if the power is odd, the sign changes. And then for 0, you look at the factor it came from, which was x squared, the power is even, so the sign doesn't change. Or you can pick points. Right? If I pick x equal to 1/2, either the 1/2 is positive, 1/2 minus 1 is negative, 1/2 squared is positive, and a positive times a negative times a positive is negative. And likewise, if you pick something like -3, either the -3 is positive. But I shouldn't even look at the e to the x and the x squared part. E to the x, always positive. X squared, always positive. -3 minus 1, oh, that's negative. So I have a positive times a negative is positive, which means it's going to be negative. So if you identify something as always being positive, you could stop thinking about that when you test points. But I don't need to consider that. It's not going to change anything. So my function is decreasing, decreasing, increasing. So I have a relative something at x equal to 1. Is my something at x equal to 1 a maximum or a minimum? Minimum. Relative minimum. Because the function was decreasing and then it was increasing. And of course I have in fact, on these sign charts, I really starting to just draw in the vertical asymptote wherever I have vertical asymptote. So what I also know is my function, this is why the first derivative is like the best part of this, really. I can see that my function is going to be decreasing down to -infinity before the vertical asymptote, and then still decreasing after, so it's going to be decreasing like this after, I'm gonna hit my minimum, and then increase after that. Cool. I guess we should find the second derivative. Yeah. Second derivative for quotients is always kind of gross. What I will say is it is usually better to use the unfactored form of your first or whatever thing to find the next derivative. I don't want to use the product rule in the numerator. Well, I'm still gonna have to use the product rule in the numerator. Maybe here that's not the best advice I've ever given. Normally I would say the unfactored form is better. Here the factored form might be better since I'm already gonna have to use the product rule. Let's find the second derivative. So bottom. Okay. The bottom times the derivative of the top. So the derivative e to the x times x minus 1, I do have to use the product rule. It's the derivative e to the x times x minus 1 plus e to the x times the derivative of x minus 1. Okay, that wasn't quite as painful as I thought it was going to be. Minus the top, e to the x times x minus 1 times the derivative of the bottom, which is 2x. All divided by x squared squared. Yeah.
Is that a question mark or is that X?
No. What next to which x where?
All the way to the left. Like, yeah.
X squared?
Oh, it's.
Sorry, no, I'm sorry. So then you shouldn't multiply anything out yet. You should look to see what you can factor. So looking at this and this, well, I see an x here and an x squared there. I can factor out an x. Also, I already knew I was going to be able to do that because I know that whenever I use the quotient rule, at the end of the day, the power in the denominator should end up being 1 larger than it was in the previous step. Since my denominator is x squared here, I know that I should be able to get to a place where it's going to be x cubed in the next step. So I should be able to factor out an x and cancel it with one of the x's in the bottom. I also see that there's an e to the x here, and each of these have an e to the x I can factor out as well. So I can factor out an x times e to the x, and here's what I'm left with. Here I'm left with x times, I factored out this e to the x here, so I've got an x minus 1 plus 1. That seems wrong, but I guess it's not. Feels wrong. And then over here, I factored out an e to the x and an x, I'm left with x minus 1 times 2. All of that is multiplied by x e to the x. It's maybe kind of annoying. Divided by x to the 4th. We can cancel or divide one of the x's here with one of the x's there. And now we should simplify what's left in here, which is again, not the nicest thing I've ever seen. We get e to the x times, oof, all right, x times x, oh, I see, okay, that, I was like, I think I made a mistake somewhere, I did make a mistake, right, there's no x right there. Let's look back here for a second. And actually, maybe I should be a little bit more clear with my steps here. No, there is an x there, I'm sorry, I'm just. I was trying to do a little bit too much at once here, so let's go back for a second and check this out. So from here, what I maybe should have done first was factor out e to the x and write this as x squared times e to the x times x minus 1 plus 1. And that would have been a little bit safer, I think. So then the x minus 1 plus 1, that just becomes x. So I really got x squared times e to the x times x. If I factor out an x e to the x, what I should be left with in here is just an x squared. Interesting. So I should have been, this x minus 1 plus 1 should have happened first. And that's kind of what I was screwing up there. Sorry. So that should be x, and then x times x is x squared. Okay. And then here we have a minus 2x, and a minus is plus 2. Ugh, kind of gross. The real gross part is that if you try to find the critical values here, you have to use the quadratic formula. Which is nobody's favorite thing to do after they've already done 12 other things in this problem. If you want to find the critical values, so that equal to 0, and we end up setting x squared minus 2x plus 2 equal to 0, and we get x equal to negative 2 plus or minus the square root of negative 2 squared minus 4 times, I think we're in luck, 4 times 1 times 2 over 2. Why am I saying we're in luck? We don't actually get any critical values. What's 4 minus 4 times 1 times 2? Right, and the square root of negative 4 is not real. So we have no critical values here other than the pseudo-critical value of 0. So here, making my second derivative sign chart, the only value of note is 0. If I pick a number larger than 0, like 1, the numerator is, let's see, e to the 1 is positive, 1 minus 2 plus 2 is positive, and 1 is positive. It's going to be concave up over here, and then over here, left of 0, well, pick a number left, like negative 1, e to the negative 1 is positive, negative 1 squared plus 2 is positive, but the denominator is negative. So concave down, concave up. It's a lot of work, especially when it's a quotient. I won't lie. The quotient does make it harder. It's a lot of work to find all the things of a graph when you're trying to find first and second order stuff. But now we have all the things we could possibly want to be able to graph it. So let's throw it all on the graph and see what happens. So looking back at my list here, I have a vertical asymptote at 0. Great, there it is. I have a horizontal asymptote to the left at 0. There it is. I have a relative minimum. Oh, there is one thing I forgot to kind of do. I do have a relative minimum of x equal to 1. I should also have found the y value. So if I go back here for a second, my relative minimum of x equal to 1, the y value is f of 1, which is e to the 1 over 1. I'm plugging that 1 back into the original function. But e to the 1 over 1 is just e. So I know that my relative minimum is at the point 1 comma e. So there's x equals 1. Let's not get too out of hand here. Let's say it's about right there. There's 1 comma e. That's my relative minimum. And then I think I've really got everything I could possibly plot. I know I have my horizontal asymptote 0, my vertical asymptote 0. Now I'm going to use my first derivative sign chart to help me graph the thing. So I know vertical asymptote 0. It's going to be going down like this. Because as I approach the vertical asymptote from the left, I have to be going down, 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 down. I also know that I have a horizontal asymptote of 0 to the left as well. So it makes sense that the graph is doing that to the left. And then between 0 and 1, the graph is still decreasing. So to have a vertical asymptote here, I have to be way, way up so that I can decrease as I move to the right of that. I'm going to decrease. And I know that this is going to be a minimum. So I'm going to try and approach it not too sharply. I'm going to decrease, and then I'm going to try and round out so that I can increase after that. Finally, after that, I'm increasing. And I'm just getting bigger and bigger and bigger. That's kind of it. Doesn't look that special considering how much work we did. But that's what we've got. Notably, it is concave down over here. It is concave up over here. You can think of concavity either as the function opening downwards, opening upwards, or what I've actually come to like is you can see it's concave down because any tangent line is fully above the graph over here. You can see it's concave up because the tangent line is fully below the graph over here. And then, just for fun, let's say someone said, no, that's terrible. Don't do that. I was going to say we should graph a tangent line, but no, we should graph a tangent line. It'd be awful. There's not a nice point. I mean, I could say, let's graph a tangent line at, I don't know, x equal to 2. So then, let's say that's 2. There's the point. Here's the tangent line. I didn't say find the equation of the tangent line. I just said graph it. So there we go. At the point 2 comma, if I plug that into the function here, it's e squared over 2. There's a tangent line. Graphing a tangent line is not terrible, typically. Finding the equation of a tangent line is more work. Times it. Okay. I'd love to do another graphing one, but I don't think we have enough time because obviously I can't do one that's fast. That said, I feel like, let's do that. Sure. Let's use our time wisely. Let's say we want to find the equation of the line tangent to, yeah, I like this. X squared plus y cubed plus e to the xy equal to, sorry, 1 second here. That's terrible. Equal to 9 at the point 0, 2. So when we look at this equation, we have to find the equation of a tangent line. To find the equation of a line, we need a point, which we have, and we also need the slope. How do we find the slope? The derivative. Right? Yes, if you had 2 points, you can find. Oh, let me just tap into my. I touched a chord. Sorry. Class is over. No, I'm just kidding. Class is not over. It's all fine. It's the. Man. You're too finicky over here. So what I was saying is we have to find the equation of the tangent line. And the way we do that is by finding the point and the slope. And to find the slope, we need the derivative. And in this equation here, to find the derivative, we need to use what method of differentiation? Implicit. How do we know we need to do that? Oh my God. Because terrible. Sorry. Because we have X's and Y's all mixed up together like that. And maybe we'll be able to do it. Maybe not. Maybe we'll never do anything ever again. Sorry. I'm annoyed at my devices here. Nope. Are you not on? Chords are terrible. So, yeah. Lovely. Brilliant. I want you to work. You just work. There we go. Perfectly in frame as usual. Okay, so you have to use implicit differentiation. Now, here's the thing about this type of problem, which I would totally ask on the test. If I take the derivative of both sides, I don't have to solve for y prime algebraically. Here's what I mean. Let's differentiate. Derivative of x squared is 2x. Derivative of y cubed is 3y squared times the derivative of y, which you can either write as y prime or dy dx, whatever you like. I guess I like dy dx. I don't actually, but I feel like it's more nice, I guess. The derivative of e to the x is e to the x. The derivative of e to the stuff is e to the stuff times the derivative of the stuff, which I'm going to do in the next step, actually, just to make it less work all at once. Equal to not 9, but the derivative of 9, which is 0. Be careful. For some reason, people tend to forget that. Like, I see people write 9 here so many times. The derivative of 9 is 0. Okay, we need to do one more step. We actually have to take the derivative of x times y. I still have a 2x. I still have a 3y squared times dy dx plus e to the xy times the derivative of xy prime. I have to use the product rule. The derivative of x is 1. Leave the y alone. Plus x times the derivative of y is the derivative of y. Y prime or dy dx, whatever you like, equals 0. Okay, this problem can swing one of two ways. If the problem then says to find the actual derivative, then you have to actually solve for dy dx. But if they're asking you just to find the slope of the tangent line, this is your moment to plug in the point. So right now, plug in x equals 0 and y equals 2. So lots of things get to go away. Maybe not lots, but some. You get 2 times 0 plus 3 times 2 squared times dy dx plus e to the 0 times 2 is e to the 0, which is going to be 1, times y plus x is 0 times dy dx. Okay, I probably wouldn't have written all that. What I probably would have written actually was, okay, 2 times 0 is 0. 3 times 2 squared is 12 times dy dx. E to the 0 was 1. I wouldn't have written it because 1 times whatever is whatever. And y plus 0 is just y. Oops, but I did forget to plug in for y. Was that what you're going to ask? Yeah, good call. I forgot. I got too focused on this over here. That should have been a 2, not a y. Sorry about that. And then we can solve for dy dx with relative ease. 12 times dy dx equals -2. Dy dx equals -2 divided by 12, which is -1/6. We're not done. We found the slope. We have the point. Now we have to put them together in whatever equation you prefer. I usually default to the point slope equation, meaning y minus the y coordinate equal to the slope times x minus the x coordinate. Here, it seems like a crime to not simplify it because you've got x minus 0. I would probably simplify this and rewrite it as y equal to -1/6 x, and then I would add the 2 over to write it in the y equals mx plus b form. But if they don't say you have to simplify it or write it a specific way, either one of these forms should be right. This feels wrong to leave it that way because again, x, you should write x minus 0 is x. You should simplify that, but either answer is correct. All right, that's all we have time for today. The plan for Thursday is to go over the practice, to go over either his practice exam or the one that I will write and post solutions to. You should sometime before Thursday, I would say, take the practice exam he has given you like an actual exam. Sit down, give yourself 50 minutes or however much time you might get. No calculator, right? Right. Whatever things you get, whatever things you don't, you don't. Don't have the solutions right there. Just sit down with the test, 50 minutes in a relatively quiet environment. No headphones, right? You don't get to listen to headphones when you take the test, I assume. All right? Take the test like you're actually taking the test. See how it goes. And then we can go over whatever you want to on Thursday, but I mean, I imagine we'll go over the practice exam. We can go over the exam I write as well. I will try the practice exam I write will be very similar in length and content to the one he has written. So I'll try to get that done today. All right, you're free to go. Make sure you fill out the attendance. Oh, the other thing I was saying about attendance is we were talking about attendance yesterday because it's important to us that we accurately count the number of students that use our services. And someone brought up a good point, which is that the more students we have that let us know that they have attended, we only have enough people doing this job for so many classes every quarter. So the ones that have more attendance get more love. So the more people that are in this class, the more likely they will be I mean, there's going to be a 16C next quarter unless something goes terribly wrong. But we just fill out the attendance form because we need to count you all. It's a small part of our funding. Please do it every time so that we can accurately count the students we are serving. Thank you.